In this video, we're going to take a look at the trend called electronegativity. So electronegativity is the ability of an atom in a molecule to attract bonding electrons. Remember, in a molecule, electrons typically atoms will share electrons to some degree, and the electronegativity is how strongly a certain atom will attract those electrons that are involved in the share. So basically, how strong is your attraction for electrons in that bond? And so one of the patterns we notice is that the electronegativity increases from left to right across a period. So, for example, fluorine would have a higher electronegativity than lithium. And then the other trend that we see is that the electronegativity decreases down a group. So lower electronegativity as you go down the group. So francium would have the lowest electronegativity in group 1, for example. Why? Let's explain trend 1 with the increasing from left to right. That has to do with effective nuclear charge again, right? So the fluorine has the greater effective nuclear charge in its periods, so that's why it would attract the electrons more strongly in a bond. Now, this trend doesn't apply to noble gases again because we don't really give them an electronegativity value because, as you know, they already have their full valence shell, so they're not really going to attract electrons very strongly in a bond. They already have their full valence shell. They're already happy the way they are. So typically, they won't have that electronegativity value given to them. So we kind of ignore them when it comes to this electronegativity trend over here. And then why is going down a group? Why is it that you have lower electronegativity over here? Well, you have more shells, more shielding, weaker attractions to the electrons, just because in a bond, those electrons will be farther away from you because of more shells and more shielding. So similar reasons for the trend that exists. And so what we've noticed is that typically the highest, the most electronegative element in the periodic table, that's kind of more to the top and towards the right side, is going to be your fluorine. It's also, very small as an atom. And that makes sense, right? The nucleus is close to the outer electrons, so there's more of a pull, and it's going to be able to attract electrons more effectively. And the francium has the lowest electronegativity on the periodic table on the other end, and that's just because it's a very very large atom, and it's more and it just doesn't hold onto electrons as tightly, and the electrons in the outer shell are so far away, it just doesn't have a good attraction for them. So, highest electronegativity on the periodic table is fluorine. Lowest is francium. There's a little bit of a debate about that. Some people say it could be cesium based on the way the electrons move around and attractions there, but based on the trend, we're not going to go with the exception right now. Francium would have the lowest electronegativity, and then fluorine would have the highest. And if you remember those positions, that basically we get higher as we go towards fluorine and lower as you go towards francium, it's a nice, easy way to remember the trend, even if you don't have the arrows drawn in. So let's go take a look at this example over here. Here we have some images to show that. We have, let's say, fluorine and silicon. Fluorine has a greater attraction for the electrons compared to silicon. You'll notice that fluorine is a smaller atom. And so because it's a smaller atom, if they're sharing electrons, the nucleus of fluorine is closer to the shared electrons, and so it would hold them more tightly, attract them more effectively in a bond. And then likewise, if we're looking at cesium and silicon, if they were sharing electrons in a bond, notice cesium is a very large atom compared to silicon. And so because silicon is smaller, its nucleus is closer to the bonded electrons over here, and so would attract them more strongly. Whereas cesium is so large, here's the nucleus, it's a greater distance from the nucleus to the outer electrons that are being shared there, so it wouldn't have a very high electronegativity value compared to something like silicon there. So just to understand that this is a relationship between size and electronegativity as well, right? So as the atom becomes smaller, its electronegativity becomes larger just because they're closer to the bonding electrons. And once again, just an important recap here, the noble gases have zero or very low electronegativity. They don't really follow that trend, again, because they already have their full valence shell. So just like we saw for all the other trends, you need to be able to answer questions regarding these trends, especially ranking elements and based on the trends and figuring out which one's higher or lower. So we'll do some sample problems regarding that as well. Electronegativity, just to mention, is going to be very important later on because we're going to be drawing molecules and figuring out where electrons like to hang out within those molecules, and that's going to be something we'll be using electronegativity. I do want to show you one more thing on our periodic table before we do some sample problems. On the periodic table we have the electronegativity is actually listed. So, for example, you can see here that we have an electronegativity of 1, and as we go towards fluorine, it increases on that side. So 1, 1.5, 2, 2.5, 3, 3.5, 4, and then our noble gases don't really count in there, at least for the first bit. They do afterwards, but those are some exceptions. We're really going to focus more on the general trend so far. So, and as you can see over here, fluorine has our highest electronegativity, and then francium has our lowest, with cesium close to that as well. Okay, there is a bit of a debate between francium and cesium. If you want, you can research that and just kind of see what the debate is. But we're going to go with the general trend of francium being the lowest, and then fluorine being the highest electronegativity value there. So let's go ahead and fill in some blanks and then do some practice problems similar to these ones over here. So electronegativity is the ability of an atom in a molecule to attract bonding electrons. Electronegativity generally increases from left to right across a period, and that does not generally include noble gases. There are exceptions, but for the most part, not really noble gases, just because they already have a full valence shell. And the reason that it increases from left to right is because there's a greater effective nuclear charge, which leads to a stronger attraction of the electrons in a bond. And also the size is related too, right? So because of that greater effective nuclear charge, the atom's smaller, and so it's able to hold the electrons closer to itself just because the electrons are closer in distance if you're sharing with another atom. And we saw that in the pictures over here. And then the electronegativity will decrease going down a group, decreases going down a group. And that's just because the more shells that you have and more shielding leads to a weaker attraction for those electrons. And it's also related to the size, right? So a larger size means your nucleus is farther away from the electrons in that bond with the other atom. So you just have a stronger hold on them. So let's go ahead and do some practice problems related to the electronegativity. So if we take a look over here, we have rank the elements by increasing electronegativity. So we have, actually, we'll do the pairs first. Pairs are easier, then we'll go back to number 1. So between calcium and gallium, here is calcium, here is gallium. Electronegativity increases towards the right, so gallium has a higher electronegativity value. Br and As towards the right, so Br wins this one. Li and O, so Li and O over here. So it looks like more towards the right is going to win again, so oxygen. Ba and strontium, so here's strontium, here's Ba. Towards the top wins this one, so strontium wins. Cl and S, so here's S, here's Cl, towards the right wins, so Cl wins. O and S, towards the top wins, so O is more electronegative. Let's go ahead and rank these according to electronegativity. We want increasing electronegativity, so smallest to biggest. So let's compare O and S first. So O has a larger electronegativity compared to S because O is more towards the top. Let's then compare Al and S. So here's Al over here. S has a larger electronegativity than Al because S is more towards the right. So Al is very small there. And then let's look at neon. So neon doesn't really count, or if it does, it has a very low electronegativity because it's a noble gas. So we would put that as our smallest electronegativity value. So neon smaller than aluminum, which is smaller than sulfur, which is smaller than oxygen. And so that there would be our ranked list. If you want more practice problems similar to that one there, just like for any of the trends that we've seen, you can click on answers here, and there's worksheets that pop up that have answers as well, and you can just challenge yourself with a few more practice problems. There's also the worksheets in the learning goals, of course. So just to recap, as we mentioned, the fluorine is the most electronegative element on the periodic table because we don't really count the noble gases very frequently. And the francium has the lowest. So fluorine highest, francium the lowest because it's at the opposite end. Cesium is very close in electronegativity to francium. So there is some debate as to which is the most reactive and which is the most metallic, and I'll explain all that in the next video, but there's a little bit of a debate between these two elements here, and you can take a look at that with some independent reading on your own just to see kind of what that debate is and why that debate exists. So in the next video, we will take a look at metallic character and reactivity.